This is MG5004 in the DE equivalent, topic 2, class 2, part 3. You'll need to advance your slides by clicking on the little box on the left hand side where it's currently showing 31. Advance that to 21. The most common type of function that you're going to meet is a linear relationship. In other words, it's a straight line, and the general format for that is y equals mx plus c. Now we only need 2 points to define a straight line, x1, y1 and x2, y2. So remember, you can use y minus y1 over y2 minus y1 is equal to x minus x1 over x2 minus x1. There are various variations on that, or you can use that y equals m times x minus x1 plus y1. They're all the same things. There's all sorts of very complicated ones as well. Let's take a couple of points. Let's take some points 5, 4 and 10, 19, and let's find the equation of a line passing through that. First up, we need to find m, so that would be 19 minus 4 over 10 minus 5, which would give us 3. So now we can put it into whichever one we like. Y equals 3 times x minus, now the x1 is 5, plus y1, which is 4, and rearranging that, we find that y is equal to 3x minus 11, and that would give us the equation of the line. You should remember that m here, the 4 in this particular case, is the m. Y equals mx, which is the slope, plus c, and c is the y-intercept. And you can see here that the first one crosses the y-axis at 5. The second one crosses it. It has an imaginary plus 0. So it's going to cross at 0. And the third one crosses at negative 3, about there. And because they've all got the same slope, they're parallel. These three graphs have the same intercept. They each cut through at 3, but they have different slopes. And just a quick reminder, if you need it, that if you've got a positively sloped line, it's going from the bottom left to the top right. If you've got a negatively sloped line, it's going from top left to bottom right. If you've got a zero slope line, and we talk about that a lot when we're in calculus, then we have a horizontal line. And parallel lines, as I've just mentioned, the slope is the same, the gradient is the same. As well as finding the equation of the line, we can also find the distance between 2 points, and this is just based on Pythagoras. So if you've got x1 and x2 and y1 and y2, then it's just Pythagoras' theorem. Just looks a little bit different, that's all. We need to be able to talk about the order of a function. So if it's got x to the power of 4, we call it a quartic function. If it's got x to the power of 3, we say it's a cubic function. If it's got x to the power of 2 as its biggest x power, then it's a quadratic. This is an invisible 1 there, so it's to the power of 1, we say it's to the degree 1, and it's linear. And this has an invisible x to the power of 0, because x to the power of 0 is 1, and therefore the power of x is 0, so we say that that is a constant function. Let's just have a quick revise over these. Let's have a look at P3. P3 is even. It's an even function because it's symmetric about the y-axis. Let's find one that's odd. P5 is going to be odd. P5 is x cubed, it's antisymmetric. So it's odd. None of them repeat themselves, so none of them are periodic. But just do a bit of revise. We can find both the x-intercepts and the y-intercepts from any curve. The x-intercept, this is where y is equal to 0, and we can find the y-intercept. This is where x is equal to 0. So you need to find those, you need to remember those for any graph drawing thing. It's really, really important, but it should be pretty basic, that the x-intercept is where y is equal to 0, and the y-intercept is where x is equal to 0. Here's a slightly odd graph. Now, if I say to you that this graph is x plus 2 over x squared plus 1, are there any values of x that we've got to exclude from the domain? In other words, is there any restrictions on x? And the answer of that is no. We'd put a restriction on x if it made the bottom line 0. But in this case, x squared plus 1 won't equal 0. So x can be anything. Can we get a negative value of the function? Well, yes, we can. We can get a negative value of the function, or of y. All we need then is for the top line to be negative. In other words, if x is less than negative 2. And you can see here that at x equals negative 2, it crosses over. We also might want to look at what happens as x tends towards, infinity. You can see if we continued this graph down, and also if we looked at the rule as well, it would tend towards 0. So we'd say then that the function tends towards 0. It's always going to be above 0. So we would say it would tend to 0 from above. Let's look at the graph on the left-hand side, R2, which is equal to t cubed minus 1 over 2t plus 3. What's the value of R2 when t is 1? So we're going to put 1 into there, so we're looking about here somewhere. And if we put 1 into the rule, then we actually get that R2 is equal to 0. So in other words, the graph cuts the t-axis at t equals 1. What if we put in t equals negative 2/3, negative 3/2? What happens then? So if we put in negative 1.5, if t is that, then on the bottom line we get 0. So the whole thing then is undefined at this point here, which is negative 3/2. So it doesn't have a value, it has a vertical asymptote. There's a value that we can't have on the bottom line. If we're looking at what happens as we approach that, so as t is approaching negative 3/2 from below, what happens? So if we're coming in this way, make it red, if we're coming in that way, what's happening? Our graph is shooting up towards positive infinity. What if we're coming in the other way? If we're coming in towards t from the right, so we're coming in this way, what's happening? The function is shooting off down towards negative infinity. And these sort of things help us draw the graph for things that we don't know what it looks like. If we look at the next graph, it's even crazier. Now we can see from the denominator that we can't have negative 2, so z doesn't equal negative 2. And we also see that z can't equal 1, because if either of those things are true, it makes the bottom line 0, which we know we can't have. So that's going to give us asymptotes at 1 and negative 2, vertical asymptotes. And what we need to do is we need to think about, and the easiest way to do it is to use your calculator and to put in some values and to have a look at what happens to the value of R3 as you approach negative 2 from the left. So you need to look. So we're coming to negative 2 from the left, and if you plug some values into R3 down here, we find that R3 is going to go positive infinity. I know we can look at the graph, but just pretend we haven't got the graph there. As we're coming from z is approaching negative 2 from above. So that means we're coming in from the right, and we just put some numbers in. We look at numbers a little bit above negative 2. We'd see that R3 is going to go towards negative infinity. Let's look at the other asymptote. So as z approaches 1 from the right hand side, so you want to get numbers a little bit closer to 1 from above, then we'd see that the function tends towards negative infinity. No, actually it's going to go to positive infinity. And as z approaches 1 from below, putting in some numbers coming up to negative to 1 from below, say 0.8, 0.9, or maybe 0.9, 0.99, we'd see that the value of our function is heading off towards negative infinity rather. And if we put all those things together, the asymptotes, we can also find where it cuts the z-axis. That'll mean that R3 is going to equal 0, and that means that only the top line needs to equal 0. And if we solve that, then we find that z equals a half or negative 1, and that'll give us those two values there. We also need to look at the modulus function. And you remember that that is defined the absolute value of x. It's got two branches. It's equal to itself if x is positive, and the opposite of itself if x is negative. Now that's all fine if we're just looking at f of x equals the absolute value of x, but what if we're looking at the absolute value of x minus 2? As with drawing any graph, we'd look at the various intercepts. We'd say when y is equal to 0, then that means that the absolute value is going to be equal to 0. And we know that if x minus 2 is positive, then x minus 2 equals x minus 2, and that's got to equal 0. So x equals 2. If we take the other half of the graph, if x minus 2 is negative, then x minus 2 is going to be equal to the opposite of x minus 2. That's got to also equal 0. So that will give us that negative x plus 2 equals 0, which still tells us that x equals 2. So what we've got is we've got one intercept, which, yeah, that's okay. Now, remembering the basic shape, it's going to be a V shape. That's the graph of a modulus function. We also need to find the y-intercept, so that's when x equals 0. So we put that in there. 0 minus 2 equals 0. So that's going to be at, that's going to be at 2. So that's 2. So what we've actually got is that the vertex here is at 0, 0, and the vertex here is at 2, 0. So the vertex has moved 2 to the right. So if we were looking at something like this, what that does, let's make it minus 4. What that does is it moves the vertex 2 to the right and down 4. So the vertex would be at 2 and negative 4, so down there. So it's going to come through something like that, and it's going to go up there. And we can use the same techniques here as we did over here. We can look at both branches of it. We can use this bit as case A. That will give us one side, and we would use that part as case B, and it would eventually give us that the intercepts were at 4 and negative 2. Some other sorts of functions that you might come up against. The unit step function, it models something where it's either on or off. And if it's on or off, it has a value of 1. So we could write it as, so if t is positive, it's on and it's at 1. Or it's off, or 0, when t is negative. So here the discontinuity is where t is equal to 0. Now we can move that discontinuity. If we look at it here, the discontinuity is at d, so we can write it like that. It's still a unit step function. It's either on or off, but it's turning on or off at d this time, not 0. In the first two examples there, the on value is 1 and the off value was 0, but it doesn't need to be that. The on value could be 2. So we could move the discontinuity and we could change the on or off values. So in the third diagram there, let's see if we can write what that's going to be. When t is greater than or equal to 3, the value of the function is 2. And when t is less than 3, then the value of the function is 0. Now we can combine some of these. Have a look at this. Suppose we've got u of t, unit step there, minus u t minus 1. Okay, let's have a look at both of these separately. This is the first one, so it would be there, that's at 1, and there, and we'll go that way. And the second one would be, so it's going to start at 1 this time. The discontinuity is going to be at 1. So at 1, it's going to be like that, and it's like that, maybe if I like that. Now the combination of that is that it's 0 everywhere except between 0 and 1, except that it's got to be less than or equal to 0 and less than 1. So it's 0 everywhere except there, if you just think about that one. So we'd show that as like that. So it's 0 everywhere else. It's 0 along here and 0 along here. But just between 0 and 1, it's going to be 1. We'll finish this section with a couple of quick circles. Circle A is the standard one. It's centered on the origin, and its rule, its function, is then going to be x squared plus y squared is equal to r squared. The next one's not quite so straightforward. It's centered on A, B. So its equation will be x minus a squared plus y minus b squared is equal to r squared. We could rearrange that and multiply it all out. So we could get that x squared plus y squared minus 2ax minus 2by plus a squared plus b squared minus r squared equals 0. And if we looked back from that, we'd see that it had a centre of a, b, and a radius of r. Now, I think the textbook uses a slightly different version. It says that x squared plus y squared plus 2fx plus 2gy plus c is equal to 0, and that it's got a circle with a centre of negative f and negative g, and the radius is equal to the square root of all of that. Which is the same as it is up there, it's just different letters. So let's have an example of that. Suppose we need to find the radius and the centre of a circle where you're given this 2x squared plus 2y squared minus 3x plus 5y plus 2 is equal to 0. So first up, let's just get the x squareds and y squared. So divide by 2. So we get x squared plus y squared minus 3 over 2x plus 5 over 2y plus 1 is equal to 0. And then by comparing the numbers on the previous slide, we'd see that 2f must be negative 3 over 2 and 2g must be 5 over 2. So that gives us that f is equal to negative 3 over 4 and g is equal to 5 over 4. So the centre is at 3 over 4, negative 5 over 4. In order to find the radius, what we're going to have to do is we're going to have to complete the square, and what we're going to end up with is that x minus 3/4 squared plus y minus 5 over 4 squared is going to be 3/4 squared plus 5 over 4 squared minus 1. So that's going to be, what's that, 9 over 8 or 18 over 16. So that'll give us that our c squared is going to be 18 over 16. So our c is going to be the square root of that, which, if you need to, you can find a number. You might be asked to find the equation of a circle that passes through 3 points. Say it passes through these 3 points. Then you know that it's going to satisfy now it's going to satisfy each of those 3 points. So it's 0, 0, 0 plus 0 plus 0 plus 0 plus c is equal to 0. So that tells us that c is equal to 0. Now let's take the point 0, 2. So now we've got that 0 plus 4 plus 0 plus 2 2's are 4, so 4g. Oops, that should be a y there. So 4g plus, we know c is 0 there. And what else do we know? We know that at 4, 0, we're going to have 16 plus 0 plus 8f plus nothing, and that's going to equal 0. Now, what we've got now is two simultaneous equations. We've got 4 plus 4g equals 0. These have to be true at the same time. Standard solution there will give us that g equals -1, f equals -2. Now, if we put all of those back in our original one, then the equation will be x squared plus y squared minus 4x minus 2y is equal to 0, and it will have a centre at -f, which would be 2, and -g, which would be 1, and the radius would be the square root of 2 squared plus 1 squared, and then c squared is 0, so that's not important in this case, so it's the square root of 5. So if we wanted to draw that, it's going to have a centre at 2, 1, and it's going to have a radius of root 5, and yeah, it's going to be a circle around there. It's just going to be a little bit, not a very good circle, but you get the idea. Oops, that's not even close. I won't even do that. I'm just going to delete the whole lot. If you were going the other way, if you knew the centre, then it would be x minus 2 and y minus 1 would be equal to r squared, which would be 5, root 5 squared. And that's what we had. We've already looked at how you can find the equation of a straight line through a couple of points. To define a quadratic, you're going to need 3 points. So there's this really nasty rule that will help us find the equation of a quadratic. It's just painting by numbers, just put in the numbers.